Hello and welcome to Enabling Storage, Space, and Avionics Applications with iWave IP Cores on our FPGAs. My name's Alicia, and I'd like to start off today by playing a quick housekeeping video.
Let's move this one here, this one over here. Oh, hey there! Before we jump into today's presentation, I want to share some cool features and functionalities of the webinar console. Guess what? It's completely customizable! Now you may only see a few windows on your screen. However, if you take a look at the taskbar below, there are various widgets you can launch to add to your screen. Boop. Take notice of the Ask Question widget. We encourage you to ask questions throughout the presentation. While our presenters are busy delivering exciting content to our audience, they are always supported by subject matter experts who sit behind the scenes and help answer questions they cannot address live. Now, grab a coffee, a pen, and a writing pad, and enjoy today's webinar.
All right, now that we've got our housekeeping items covered, please take a moment to access the menu bar at the bottom of your screen to see all the engagement tools we have available for you to use throughout today's session. Also, as a reminder, this session will be available for you to rewatch on demand. In today's session, we'll be partnering with Deepak B, Chitan TV, and Tawfiq Ahmed from iWave. Tawfiq will be kicking us off today, so Tawfiq, please take it away.
Thanks, Alicia. Good morning, good afternoon, good evening, everyone. Thanks for joining us from across the globe. And welcome to a webinar titled Enabling Storage and Avionics Applications with FPGA, iWave, FPGA IP Cores, and ODM Expertise on Microchip FPGAs. So what is it we are going to cover in the next 45 minutes? So a quick introduction of iWave, an overview of our FPGA expertise, and the Microchip partnership over the years. And then followed by an ODM expertise, where we have enabled customers with various types of ODM solutions, followed by our Arinc IP cores and storage IP cores, a few case studies, and an overview of solutions, followed by the licensing models from iWave and the technical support models from iWave to help customers in their product development. And last but not the least is in terms of what sets iWave apart and what helps customers choose iWave. So iWave, to give you a quick background of iWave, we are a 25-year-old company. So we started in the year 1999, and over the last 25 years, we have been driven by the mission to be the trusted embedded technology partner to companies across the globe. And over the last 25 years, we have been building on our core competency of embedded systems design and product engineering. And iWave is driven by the pillars of innovation, quality, and trust. And with this core competency and these driving pillars, we have a strategic focus on serving customers in the industrial, automotive, medical, avionics, and defense vertical markets. So all our embedded expertise and our core competencies are built towards catering towards these specific vertical markets. And I'm proud to say that over the last 25 years, we have enabled close to 1,200 products across 35 plus countries. And how do we do that? So this is because of the compelling presence we have across the globe. So our engineering headquarters based out of Bangalore, India, our financial and logistics headquarters based out of Dubai, and then a sales footprint across the globe, ranging from Germany, California, Korea, Taiwan, and Japan. And this is how, with our engineering headquarters and a global sales footprint, we have been able to support global customers. And also, this wouldn't have been possible without a robust and well-established manufacturing ecosystem. So the last 20 years, we have had a very good established manufacturing ecosystem in Japan, from where we have been serving customers worldwide. And now we are expanding that manufacturing ecosystem to North America, Taiwan, and India. And giving an overview of the iWave Microchip partnership over the years. So iWave has been a part of Microchip's FPGA design partner network, and we have built a strong FPGA design to deployment competence team. And Deepak and Chetan, who are along with me on this call, have led a corresponding FPGA team, which has enabled customers from this design to deployment to production. And we also enable customers on RTL design, integration of iWave IP cores, or third-party IP cores on the Microchip FPGA portfolio. And last is in terms of different types of carrier card design, board design, custom hardware, and product design depending on specific customer requirements as part of our ODM model. And if you look at the bottom of your screen, the Arinc towards the avionics market, SFPDP, storage, bridge, and x86. So these are our portfolio of IP cores, which we'll also cover more in detail through the course of this webinar. And our FPGA team is driven by this corresponding mission. So we are committed to relentless innovation, offering proven and easy to use FPGA IP cores, which are targeted towards low power, high performance, and optimized designs to accelerate application development across all key markets and enables customers to focus on their application development and their core competency. So this driving mission statement has been a key success factor for us over the last 25 years and continues to be the driving force going forward. So as a company, we also focus on ODM, right? What is ODM? It is original design and manufacturing, where we enable customers from ideation to production. So starting from specification analysis, requirement analysis, to the next stage of drafting block diagrams, doing the hardware design, taking care of the intricate aspects, the power analysis, signal integrity, the high-speed board design, and the complete the product design, followed by samples and functional prototypes, and then the production qualification, certification, and production, and supporting customers over the complete product lifecycle. So that is where iWave comes in. We are not a SOM vendor, we are not a hardware vendor, but we are an ODM partner to product development companies across the globe. And now I would hand it over to Chetan, who can take you deeper into the FPGA solutions and IP cores expertise. Over to you, Chetan.
Thank you, Taufik, for the overview about iWave. Hi all, this is Chetan. I'm an FPGA guy. I spend most of my time and space in managing and designing. In the process, I'm in charge of the team who does design and development for defense and aerospace, which is the main point of discussion in today's topic, and RTL development on NVMe storage and video applications. And also we are presently working on some niche technologies on Rocky V2 for our data center applications. With this, let's get started with the technical part of the webinar, where I'll be discussing about two topics today. Firstly, iWave's technical expertise in FPGA domain, and then comes Arinc 818 IP cores and the iWave solutions around it. So you're seeing the FPGA expertise at iWave on the screen. So as technology investors and technology solution providers, we are one of the early starters when it comes to FPGA design and development. We were able to foresee the potential of FPGAs and how it can fit in providing solutions to the challenges posed in today's market. We are working on FPGAs from the past 20 plus years, and we have a very mature team with these listed skill set. So we have branched our team into 4 different domains or branches: hardware, software, and FPGA. And we have also RTL expertise as well. Hardware team, they have expertise on high-speed designs, analog and RF designs. Software team, we have expertise on complete development lifecycle of software lifecycle like BSP, driver, application, OS, and non-OS development. And also we are honing our skill set in the smart HLS, where one can rapidly develop the complex algorithms on FPGAs, taking the advantage of C abstraction. And then comes the FPGA team, where digital design and RTL is our core capability, with expertise in VHDL, Verilog, and System Verilog, both in design and verification. And other subject matter expertise on complex architectures like high-speed transceivers and memory designs, analog and mixed signal integration, STA, CDC, and architecting for power, area, and speed, and so on. With this, I'll go to my next slide. With the intention of having complete end-to-end ecosystem, where we have equipped ourselves with these latest tool set for to assist us in design and development and debugging. So you can see the EDA tools for the FPGA synthesis, simulation, PNR, and timing closure, hardware simulation tools for SI and PI. With the advent of high-speed transceivers running at 112 gigs and upwards, we will be requiring these tool sets. We also have hands-on on the almost all the family of the FPGAs that are listed here. We also have in-house thermal and humidity chambers for environmental testing and pre-compliance. And I have also listed few of our IP cores here, which we'll be discussing in the coming slides. So these are the FPGA domain expertise what we possess. I have listed it extensively in the slide, but I'll be mentioning few notable points here, like PCIe, serial and express protocol standard, storage like NVMe, SATA 3.0, eMMC, SD, NAND, and video domain, analog and digital video standards. And we also do possess some comprehensive video processing IP suites. And ADC and DAC, data capturing over LVDS or JSD204B. We have done time domain, frequency domain, sample analysis, and signal processing. With this, I conclude my iWave expertise part, and I'll be moving to the iWave Arinc 818 and iWave solution around it. So basically, what is Arinc? It is an acronym for Aeronautical Radio Incorporated, and it is the name of an organization or corporation. We are familiar with FCC, that is Federal Communication Commission. It's an independent agency who regulates the communication from devices or equipment like radio, television, or satellites. And FRC, which is Federal Radio Commission, is the predecessor of the present-day FCC. And this FRC, they chartered Arinc Corporation to serve as airline industry's licensee and coordinator for radio communication. And they also maintain standards for LRUs or line replaceable units, which are basic building blocks in an aircraft communication. And Arinc, which was established long time ago, I'm talking the timeline of 1929, almost a century back. And Arinc as a company has evolved over the years and has gone through multiple mergers and acquisitions with other aerospace organizations, and so has its roles and responsibilities have also changed, which are to promote safety, efficiency, regularity, optimization in an aircraft operation. And aeronautics industry has to be governed by C-of standard to function precisely, and Arinc has defined and ratified few of those standards, around 80 of them, which are categorized into 5 series from 400 to 800, where each series address a unique set of guidelines or standards. Today we will be discussing about 2 of those standards, one from 600 series, other one from 800 series, namely 664, which is also known as AFDX, and Arinc 818. Before getting in depth into the protocol, let us try to understand the ecosystem of video in an aircraft. So Arinc 818 is primarily a video bus. It is all about how you transport video from one system to another system in an aircraft. There is no video generation or video processing included in the protocol per se. It is only the transport. But there are advancements in the protocol that have been done where even non-video elements as well are transported. And let's get started with the video initially, and then we'll see how the other data were appended into the protocol. So why do you need video in an aircraft? There are various video systems involved in an aircraft which are used for critical operations such as navigation, target tracking, collision avoidance, and there are some less critical operations like taxiing or infotainment and cargo loading. So for all these things, we'll be requiring video. On your left side, you can see a pictorial representation of Arinc 818 system architecture. For simplicity, I have just categorized into 2 things. One is the DU and the other one is mission computer. Mission computer is the intelligent part that does video capturing and processing. And then comes the display units, which presents these processed information from respective function onto the cockpit monitors. On the right hand side, you can see the block diagram representation of the system architecture. It illustrates how various systems of an aircraft comprising of video sources and video sinks are interconnected to each other. Video sources are basically optical cameras, IR sensors, and pods, and avionic image function, which you are seeing a lot of blocks in the representation. These are the devices which does video processing or video forwarding. The input to these functions need not only be from the video sources. Various information comes from the indicators, which are converted into images with the help of processing units, and then these images are then pushed into the DUs. For example, flight recorder, map or chart subsystem, synthetic vision subsystem, or video concentration and distribution subsystem. Video sinks are display units. There are various types of display units like HUDs, HMD. I'll be discussing these things in the next slide. And one more point is all the flow of data between any video source to video sync is always unidirectional in Arinc 818. This slide talks about video syncs or the DUs, what I just mentioned in the last slide. The avionics architecture is very complex and critical both in function and design. Captain or the pilot need to control a lot of instruments and systems installed throughout the aircraft by monitoring the inputs from the sensor or pods that are pushed to the displays. That is the reason cockpit looks like the way it looks. Just to let you have an imagination, there are around 250 switches or buttons in an F-35 fighter aircraft cockpit. And the pilot needs to use them judiciously for the mission effectiveness. And as engineers and technology makers, we have to make the job of the pilot less difficult and assist him in pushing the right button at the right time. Please refer the image civil aircraft cockpit image just to understand how complicated a cockpit setup would be. And cockpit displays can be broadly categorized into three types: HUD, HDD, and HMD. HUD is the heads-up display. It is installed basically in line with the pilot's line of sight. It consists of critical information like situational awareness data. You can refer to the figure fighter aircraft cockpit, where you can see a trapezoidal display, which is also transparent, so the pilot can see through it. The advantage of HUD is pilot need not divert his attention from his outer environment to view the information on the display. It is very critical to have active during the active flight missions, where decisions have to be made in millisecond accuracy. And then comes the HDD or heads down display. This is below the pilot's field of view. These are conventional panels with comprehensive flight information. It is of two types, basically PFDs and MFD. PFD is primary flight display. It consists of essential flight parameters, and MFD is multifunction display. It is a customizable display where pilot can have his own layout of information to be displayed. He can pick and choose based on the mission that he'll be taking. Refer to the image fighter cockpit with the two green color square which indicate PFD and MFD below the pilot's line of sight. And then comes HMD, which is helmet mounted display. This has a display embedded into the helmet screen where even the pilot, even when he changes his direction of sight, information will always be there. It carries very critical emergency information and some binocular visions as well. You can notice that a reticle here in the advanced glass cockpit which moves along with the pilot's head direction. With the upgradation of aircrafts from generation to generation, like Gen 1 to Gen 5, displays have also been upgraded from analog indicators to CRT displays to digital LCD displays. Here, I'm not talking about analog video and digital video. It is analog indicators to digital displays, like moving from an analog watch to digital watch. It is the same information, but in a better way of representing. In this image evolution of equipment, you can just see how it blends the information from 6+ indicator to a single display. This is a PFD display. And you can also refer the glass cockpit image in an F-35 aircraft. It has completely redesigned the way information is presented to the pilot. Coming to the Arinc 818, like I defined earlier, 818 is a protocol standard for high bandwidth, low latency, low overhead, uncompressed digital video transmission in an aircraft. So with this definition, you can notice that there are some strong terms which are used in the definition. So basically, how do you measure or quantize these wordings that is defined? So high bandwidth, it supports up to 28.05 Gbps per lane. For example, a 4K video at 60 FPS with RGB 888 24 bits per pixel requires only 12.5 Gbps, including the protocol and encoder overhead. And low latency, this is a very implementation specific term based on how the implementation has been done by the engineer. Some people will use frame buffers, and some will use line buffers, and some will use even less memory elements in the path. So the equipment which does the image processing demands frame buffers like overlay or fusion. Other equipments which does only switching or video parsing will use only line buffers. And here, why latency is important? Latency is directly proportional to how fast you can put the information, critical information, on pilot's display. Also, deterministic latency is a critical factor here. All these sensors should be coherent. That is, if different sensors have different individual latencies, there won't be coordination on the, and it will lead to the information mismatch for the processing. Also, information on the HUD and actual pilot's vision outside the aircraft should match what we saw in the last slide, else it will lead to an imbalance and disturb pilot's equilibrium, and it will lead to a medical condition called vertigo. And the next terminology here is low overhead. Protocol has very low overhead, around 5%, and there will be an additional overhead based on the encoder that is used in the implementation, like 8B10B or 6466 or 127, 128. And next term is uncompressed. Why it has to be uncompressed? The reason, because there is no compression without any loss, and loss of data is non-negotiable in aircraft, and every bit of data will become important at some point of time for future analysis. Arinc 818 is based on FCAV, which gives option for compression, but it has to be selectively adopted based on the criticality of the information under consideration. I will discuss about this again later as well. So the next question that comes to mind is, what does it solve, or why another new protocol or standard? Why can't we use something that was already present? So let's analyze what are the other standards that we have. Analog standards like NTSC, PAL, VGA, STANAG, and so on, and digital standards like HDMI, DVI, DP, Ethernet, and so on. Even the standards, every standard that have listed has one or the other limitation. Some has limited bandwidth due to the physical transport on which it is running, and some operates in parallel bus interfaces, and some of these standards does not provide deterministic latency, which is a hard requirement in avionics application, and some of the interface standards will not provide the necessary robustness required for this rugged environment in the field of deployment. And there is no aggregation support. For example, there are n sensor data has to be moved from point A to point B in an aircraft. Typically, you need n individual lines of transport, physical transport. Instead, in Arinc 818, you can take all this over a single high bandwidth capable link over a single loom. It is called as multi-stream over single link, and it will help optimize the length of the physical transport, and it will also assist in swap. Another reason for the new standard was there was no prior standardization. Many equipment manufacturers had developed their video systems with their own standards and interfaces. It led to interoperability issues during final system integration in an aircraft, and it led to the use of additional converters to convert from one protocol or standard to another in an aircraft. This adds additional weight and power, and it will also lead to loss of data whenever that conversion happens. And all these led the Arinc committee to baseline and consolidate proprietary standards and develop Arinc 818, keeping the FCAV as its base. And what are the salient features of 818? Flexibility. Arinc 818 is less rigid and more implementation specific, and has a lot of room for customization, and ICD carries all this information. And scalability, it varies from FC1X to 32X. It supports multi-stream, that is multiplexing multiple video stream over single high-speed link, and the capability to drive two links, drive a display from two links. So this is basically added where a single link does not have the adequate speed to carry that much of data. And then comes the integrity. It supports CRC error checking at ADVB frame level as well as image level. So what are the variants and specification references in Arinc 818? ADVB, which is basically Avionics Digital Video Bus, was officially ratified as Arinc 818 in the year 2006. With all the features what I explained until now, Arinc 818 was considered as de facto standard for carrying the video in an aircraft. From 2005 up to now, say it's almost 2 decades, Arinc 818 committee has revised the specification twice after its initiation. With these additions, Arinc 818 is not only considered for video display interface standard in aircraft, it's rather also being evaluated by other domains like medical, marine, and automotive sectors. Arinc 818-2 was ratified in 2013 and added certain features like higher speeds, basically 6x, 12x, 16x, 24, and 32x. And it also added 5 Gbps in order to support few FPGA SerDes with the non-fractional line rates. And video processing such as compression, encryption, switching, or networking. With the increase in the amount of data, compression was hard to resist for applications with limited storage, and encryption was added to protect the sensitive data. And then comes channel bonding and region of interest. And 818-3 was ratified in the year 2018, and there was an addition of 6466B encoding to support higher bandwidths, which was the major addition, and also provided mapping for each line rate to a particular encoding and decoding. And there was a stress on multi-stream and addition of latency budget in 818-3. So Arinc 818 refers to other Arinc series specification as listed here for physical medium transport to ensure interoperability and performance. These are 801 to 806 listed here. 2 are specs for connectors and cables, and remaining 4 are reports. Transmission medium. Arinc 818 basically is based on FCAV layers. As per FC0 physical layer, there is no constraint on the physical transport on which ADVB has to run. It does support optical as well as copper, and people are now discussing even wireless. So there is no constraint from the protocol itself. Copper is easy on installation, but feasible for limited bandwidth and length. Also, EMI, EMC, and susceptibility to crosstalk is a huge concern. Copper. You can see the images pictured here. Connectors and cables from various manufacturers and form factors are available in the market, like Twinax, Quadrax, or Octanet, and so on. Shielding and impedance characteristics plays important role in selection of a copper medium. And when it comes to optical, options like multi-mode, single mode at 1310 nanometer and 850 nanometer wavelengths are also available. So iWave's Arinc 818 IP cores, these are the iWave's suite of 818 IP cores. These IP cores can be implemented on any FPGA that provides the required SerDes rate. There is no limitation from the IP core itself. Let me explain each of them separately in the coming slides. This is a 818-2, 818-3, and switch. 818-2, it is compliant to -2 spec standard. It consists of both transmitter and receiver. If you're looking at the image, there are micro architecture RTL blocks are constituted in the IP core, like packers, buffers, framers, and deframers. And detection and error reporting through sideband signals and register set logging. Simple streaming user interface for video data. Configuration of the IP and its register set through simple lightweight interface. And on the serial side, it will be integrated with the device SerDes transceiver block itself. And -3 is compliant to -3 spec standard. And major addition here is 32X with 64/66B encoding. And this is the Arinc 818 switch IP core, which we possess. This is a 12x12 low latency synchronous switching. It does, and it supports multiple modes like broadcast, unicast, multicast. So broadcast is 1:all, and unicast is 1:1, and multicast or mixed is basically any to any. iWave do provide ready IP evaluation and reference design on Microchip PolarFire development kit. Below are the links to the article and video demonstration, which explains the same in detail. I'll be sharing the same for future findings as well. Like explained earlier, iWave has developed a suite of Arinc 818 products around the IP cores to provide off-the-shelf solution in the aviation market. So we have video conversion COTS module, which does conversion from HDMI or DVI to Arinc 818 and vice versa. They come in different form factors and configurations like PCIe, 3U VPX, 6U CPCI, and based on the number of channels, single or dual, and so on. And you have an 8x8 switch that is any to any low latency switcher, and you have an Arinc monitor, Arinc recorder, and Arinc protocol analyzers. All this product comes with a configurable ICD, configurable ICD option using a GUI suite, and these also include test bench solution as well as flyable solutions. All the product do support optical and copper, obviously copper with limited bandwidth and optical with full bandwidth. So what is the support that is provided for these IP cores? iWave IP cores are developed and upgraded parallel to the Arinc 818 spec roadmap, and also validated in various platforms and tested for interoperability against multiple transmitters and receivers available in the industry. And ICD support, which is the interface configuration document. 818 is very agnostic at many places with respect to implementation methodology. Hence, ICD should capture all the necessary information and play an important role. iWave can assist customers in defining defining the ICD for the requirement. And certification is very critical for acceptance of avionics systems. iWave has hands-on and do provide necessary artifacts to get the product certified for DO254 equivalent certification, that is assurance level DAL A and B. So why Microchip FPGA? This is the last slide which I'll be covering. So the challenges that are involved in space and avionics application are basically high reliability, robust security, and low power. And the advantages of using Microchip FPGA is a commitment to the product longevity and inbuilt anti-tamper features of the devices to protect the equipment from the threats that is basically data integrity, and its power efficiency, and rugged thermal environment in the field of in this field demand for advanced ruggedized defense packages. With this, I'll conclude my part of the webinar. I hope this information will assist you in architecting your systems on Arinc 818, based on Arinc 818. And that's it from my side. I'll hand over it to my colleague, Mr. Deepak, for more interesting topics. Thank you.
Thank you, Chetan, for sharing the details on Arinc 818 related offerings. Hello, everyone. I'm Deepak, working as Associate Director in the FPGA team at iWave Global. I'll be starting with Arinc 664 end system IP core and then continue with the various storage IP cores that we offer to our customers. So as an overview of Arinc 664, Arinc 664 Part 7 standard adopts the key elements from AFDX to standardize a deterministic network for aircraft. It is based on IEEE 802.3 standard and works either with 10 Mbps or 100 Mbps rate. It uses a special protocol to provide deterministic timing and redundancy management. Coming to the network topology, it works as a network rather than a bus. There are two types of devices on the network: switches and end systems. So our IP implementation is about end system, and end system exchanges the data through virtual link. A virtual link is a unidirectional connection from one source end system to one or more destination end system or end systems. The end system controls the flow of each virtual link according to the bandwidth allocation gap, or what we call it as a bag. So bag can have multiple values ranging from 1 millisecond to 128 millisecond. Redundancy is one of the key feature which is achieved by duplication of the connection, and frames are transmitted concurrently on both the network. At the receiver, invalid frames are discarded by the integrity checker, and the concept of sequence number check is used for this purpose. As you can see, the typical use case of Arinc 664 end system IP core is presented here. The various sensors, controllers, actuators present in the system will be acting as a data source, and these data is then fed to Arinc 664 end system, which communicates from one end system to another end system using either point-to-point connection or through a Arinc 664 switch. So as I mentioned previously, our IP implements an end system, and the following are the key features of this IP. IP supports 8 transmit and receive ports. Actually, it is a scalable based on the customer requirement. IP implements the redundancy functionality at the TX side, and at the RX side, it implements integrity checker and redundancy management. IP supports a back timer from 1 millisecond to 128 millisecond. At the user interface, the IP supports AXI stream interface for data transfer and AXI Lite interface for register configuration. That was a brief description about the Arinc 664N system. Next, I'll take a look into various storage IPs and its use cases in further slides. So our storage IP core expertise starts right from the NAND flash controller and extends all the way up to NVMe host controller, which is currently under development. Just to begin with the NAND host controller, this IP provides an easy interface to access the NAND flash device. This IP forms a bridge between NAND device and user, enabling the user to program, read, erase the data in the NAND device. IP supports both asynchronous and asynchronous modes of operation with up to 16 kilobyte of page size, which is compile time configurable based on the page size of NAND device. It supports all mandatory commands, and also the IP allows user to enable either hardware ECC or software ECC or on-die ECC based on the user application. Hardware ECC supports the BCH code, which can support up to 60-bit of corrections. So NAND host controller finds the best use in application like small size satellites, where our IP allows the data from various sources to be written to non-volatile NAND memory and read back later based on the application. It also finds the application in defense and space, where our IP already being used. So the NAND flash IP core available in various configuration to meet diverse requirement of different customer applications. In the first variant, NAND Linux driver implemented in the RISC-V core of SoC device, and NAND host controller is implemented in FPGA. In this variant, we support well-known industry standard flash file system like JFFS2 and UBI. The next variant is like a simplified bare metal driver for SoC or non-SoC FPGA devices. In this variant, bare metal driver is implemented in RISC-V core of SoC or soft core instantiated in the non-SoC device. Bare metal NAND driver supports NAND device initialization, basic erase, program, read operations required for proving the IP functionality. We also support simple test driver variant for non-SoC FPGA devices, where the test driver implemented in the FPGA will execute, erase, program, and read operations to prove the functionality. Our NAND IP is recently validated in PolarFire video kit, where we tested file system variant of the IP using our FMC daughter card. So the next storage IP is SD or SDIO host controller IP. This IP interfaces with the SD driver and translates them into the cycles as per the SD protocol and enables the communication with the SD cards and SDIO based devices. The SD system comprises of SD driver, which will be typically implemented in the hard core or soft core. The SD host controller will be implemented in the FPGA, and SD card connected to the FPGA through hardware connections. So if you look into the features of this IP supports single and multi-block data transfer with the block length up to 2 kilobytes. IP also supports the various modes right from default speed, high speed, SDR12, SDR25, DDR50, SDR50, and SDR104. The support of the modes like DDR50, SDR50, and SDR104 are subjected to target device I/O capability. So looking at the application of this particular IP, this IP finds its place mainly in data recording applications, where the data from different source can be stored onto a SD card using this particular IP. This IP also serves as a secondary SDIO controller in SoC FPGA devices. Typically, the primary controller of the SoC can be used for the booting, while the secondary controller implemented using our IP can be utilized for other storage requirement of the system. So something similar to NAND flash IP core, the SD host controller also comes with a couple of variants. Again, the first variant is like with the file system, where like a SD Linux driver will be implemented in RISC-V core, and SD host controller is implemented in FPGA. In this variant, IP supports device partition, mount, and multiple file system like FAT32 and ext4 with the MBR and GPT partitions. Second is the simplified bare metal driver. In this variant, the bare metal driver, SD driver, will be implemented in either RISC-V core or like a soft core instantiated in non-SoC FPGA. Bare metal SD driver supports SD card initialization, basic write and read operation required for proving the IP functionality. And the customer can develop their own end applications based on the API that we provide. So moving on, the next IP is eMMC host controller. This is very similar to SD host. The eMMC system also includes the eMMC driver, host, and device. Driver will be typically implemented in a hard or soft processor core, whereas the host gets implemented in FPGA and interfaces with eMMC device. Looking at the features of eMMC IP, it supports single and multi-block data transfer with the 2K block length. Operation modes includes default speed, high speed, SDR50, DDR50, HS200, HS400, and HS400ES. Again, in this case as well, the support for high-speed modes like HS200, HS400, and HS400ES basically will depend on the target device. IP also supports command queuing engine as per the eMMC 5.1 specification, and similar to SD host, this also finds its applicability in data recorders as well as to enable the secondary controller in SoC devices. Again, the IP variant is very similar to SD host. So the file system version runs on the eMMC driver in the RISC-V core and supports device partition, mount, and multiple file systems, something similar to SD. This IP also find available with the simplified bare metal driver, which finds its ideal use in non-SoC FPGA devices where we can provide our reference APIs. Next is like SD memory device controller. Coming to SD memory device controller IP, this IP implements SD card functionality in FPGA, which responds to the commands from the SD host and enables the communication between SD host and user logic. The key feature of the IP include IP supports both 1-bit and 4-bit data with 512 bytes of data block length. Core handles the SD protocol on the card interface and also handles all housekeeping tasks by itself without user logic intervention. IP supports standard and high capacity operation, and card capacity can be defined based on the memory available at the user side. So application of the SD memory device controller. Primarily, this IP is used in the mobile security engines. I will discuss more about this use case in further slides. This IP also finds its use in drone application. In this case, our IP interfaces with the SD host, which is part of the camera system, subsystem, and collects the data from multiple cameras for further processing. So looking at the variants of this particular IP, the first variant is a simple user interface with the block RAM of FPGA targeted as a memory, where the capacity of SD depends on the block RAM available in the target device. In the second variant, it comes with the bare metal version with the DDR connected to FPGA as a target memory, And again, the capacity depends on DDR size supported in the target board in this particular variant. So both variant supports device detection, and the user can execute raw read, write using DD commands, what is supported by the Linux. So moving on to next IP, let us look into the features of SD host controller. This particular IP supports rich set of FIS types in the transport layer and primitives in the link layer. This IP uses the transceiver from FPGA vendor for physical layer implementation, and this is suitable for interfacing with the SATA-based SSDs and HDDs. The IP variants also something similar to our other IPs. In the first variant, where like the file system based, the SATA Linux driver is implemented in RISC-V core, interfaces with the ASCII controller implemented in the FPGA, and the ASCII controller then communicates with the SATA controller using AXI stream interface. This variant supports device partition, mount, and multiple file system like FAT32, ext4. We also support test driver variant for non-SoC FPGA devices. The test driver performs the write and read operation and checks the data integrity to prove the IP functionality, which can be controlled by the soft core. So along with our SATA IP, we do have a SATA bridge controller, which provides a bridging feature between the SATA host, which can be a processor or the host PC, and the SATA device. SATA 3.0 bridge controller acts as a device towards a host and acts as a host towards the SATA device, thereby enabling the communication between them. Highlights of SATA 3.0 bridge controller includes independent SATA host and device speed negotiation with the negligible performance degradation. It supports hot plug and safe eject handling. IP implements the command extraction logic and FIS extraction logic, and this allows the user to have the customizable encryption and decryption logic. Looking at the application of SATA bridge and the SATA host IP cores, it finds its place mainly in the various applications like digital video recorders and network attached storages, or what we call it as a NAS. Our SATA bridge IP core used to build secure SSDs, where our IP allows the user to run any kind of encryption and decryption engine, thereby enabling the secure communication. So this was all about the storage IP cores. Now let us go through a couple of use cases where like we successfully used Microchip FPGAs in our custom designs. The first use case is about MIPI CSI to TX and RX subsystem, where dual polar fire FPGAs are being connected to MIPI sensors, and data from these sensors are captured, pre-processed, and transmitted to IMX chip over MIPI CSI TX interface. MIPI CSI to receiver of IMX receives the data from both FPGAs simultaneously and transfer it to the host PC for post-processing over 10G Ethernet interface. Our scope in this design was to develop the FPGA and software logic. Microchip's polar fire FPGA is being used in this design, along with the MIPI CSI to TX IP core from Microchip. iWave's expertise in MIPI TX and RX, RTL coding, and software driver development played a very crucial role in achieving the final result within the defined timeline. So the other use case is based on the SD memories device IP in the area of mobile security engine. In this case, IP receives the data from SD host and passes to the microcontroller, and we implemented wrapper module in order to enable the communication between microcontroller and FPGA. The microcontroller implements security algorithms, and then writes the selective data to the flash memory. The low power Igloo device from Microchip is used for this application. In this use case, basically iWave not only supplied the IP core, also helped the customer to customizing the IP as per their requirement. This is achieved with our domain expertise of RTL coding, software driver development, especially bare metal code in this particular case. So finally, the ultimate question would be why someone should choose iWave. To answer that, we have well-proven IPs. Those are tested in multiple hardware platforms and already licensed to multiple customers across the globe. We offer flexible licensing models, also support for customization around IP cores, which is one of the unique advantage that we provide. We are also equipped with all required development tools and design for design and development. And looking at different licensing model that we offer, we basically license the IP either in netlist format, which will be specific to the customer target device, or the other option would be like RTL license, where we provide the source code of the IP to the customer, and they are allowed to modify as per their requirement. The licensing model will also depend on whether it is targeted to single project or multiple project, also whether it is used in the single site or multiple sites of customer organization. So coming to support that we offer, iWave being best known for its support, we provide comprehensive support during the system integration and validation at the customer end. We provide the support through phone, email, or online meetings, and we provide remote debugging support as well to address the customer pain point. So just to summarize, what sets us apart from our competition? Our decades of extensive experience in FPGA technology, which guarantees the exceptional solutions. We have all tools required for seamless FPGA development. We are trusted by the major players in avionics and defense industry. All our IPs are available in flexible licensing model options, and we provide the 24/7 support. So just before we wrap it up, here is a testimonial that we received from AES on one of our custom design. And there are many such happy customers who have appreciated our designs and support. You can also find few links that talks about different implementation and use cases, which you can download after we share this presentation. So thank you everyone for your valuable time, and we are delighted to collaborate with you to serve you with our ODM and various IP offerings. Please note that following this, we will have a Q&A session. Please post your questions, and we will do our best to address as many as possible. Thank you. Over to you, Alicia.
All right, thank you, Deepak. We do have a couple of questions that came through during the presentation. So I'm going to get us started quick. We might not get to all of them, but we'll have a few here that we can answer in our time slot. So the first question is audio can be sent along with videos in Arinc 818?
Okay, let me take this question regarding 818. Yes, the answer to this question is yes. We can send object in object to both audio as well as video can be embedded, and it can be transported in 818.
Thank you. Next question we have here is, can SATA host be implemented in PolarFire device?
Yes, to answer that, yes, our team is already working. We have done the feasibility, and we should be able to implement SATA host in PolarFire devices.
Awesome. And then we're just going to do one more question here. Is there any limits for installing any of the iWave IPS multiple times in the same design?
Okay, there is no limit basically, like the customer can instantiate our IP any number of times in the single design.
Awesome. All right, well, I think that is all the time that we have for today. Again, thank you to iWave for joining us for this presentation, and thank you to our audience for attending our session. We ask that you please take action on your screen to see all the exciting webinar content we have coming up. Thank you and see you soon.